Chapter 5, Electrons and Atoms. 5.1, Revising the Atomic Model. Now, Rutherford's model was the first that had the nucleus in it, but it only explained a few simple properties of the atoms. It could not explain chemical properties of the elements. So one of his students, Niels Bohr, in 1913, started to try to incorporate newer discoveries about how the energy of the atom changes as it absorbs or emits light. Each electron orbit in Bohr's model has a fixed energy, so he came up with energy levels. The energy required to move an electron from one level to another is called a quantum of energy. And he also stated that the electrons cannot exist between energy levels and that the energy levels are unequally spaced. The higher energy levels are closer together. Now, what Mr. Rutherford could not explain, but Bohr could, was the fact when you add energy to elements, they gave off colors. So if you were to take an element that was, let's say, at the first level, ground state, and give it enough energy to jump it up to the third level, you would get violet light from it. If you had an element that was going from an electron from a second level to the third level and falling back, it would give off red light. So here it is. So we have an electron, N1, N2, N3. Ground state, excited states. So the electron in N1 gets hit with energy that's at the red wavelength. That jumps it from 1 to 2. As it then falls back, it gives off the same amount of energy it absorbed. So as it falls back down, it's going to give off the same red light that it absorbed in the first place. Let's say we get more energy. Let's say we're going to take that from the first row, or I should say the first level, giving it some violet energy, which is higher in energy, to jump it all the way up to the third, n equals 3. So at that point, it's going to fall back down. And when it does, it will give off the same color that it absorbed. So that would be violet light. So that's what Rutherford couldn't explain that Bohr could. So, of course, things aren't going to stay that way. 1926, Erwin Schrödinger devised a mathematical model of the behavior of an electron in a hydrogen atom. And what you're seeing there on the right are his equations. From his equations, he came up with what's called the quantum mechanical model. And it's the modern description of electrons that came from his calculus equations. Like the Bohr model, the quantum mechanical model restricts energy of electrons to certain values, so it kept the energy levels. But unlike the Bohr model, the quantum mechanical model does not specify an exact path that the electrons take around the nucleus. His model came up with a probability of finding an electron in a certain area, which he called a fuzzy electron cloud. Using his calculus and his equation, you could then find the area where you can find an electron, not necessarily where you're going to find it, but where it could be, where it probably is, and he changed the word atomic orbit to orbital. He also said that there are 7 principal quantum numbers, 1 through 7. And he said the energy levels are made up of up to 4 sublevels. The sublevels are S, P, D, and F. There's 1 s orbital in the s sublevel, there's 3 p orbitals, there are 5 d orbitals, and there are 7 f orbitals in each sublevel that contains them. Each type of orbital has a different shape due to Schrödinger's equation. So, the s orbitals are spherical like the yellow one. The 3p orbitals are dumbbell shape or hourglass shape. And the 5D are mostly cloverleaf, and the fourth one, or I should say the fifth one, is a different shape. The f orbitals are just complex. We're not going to give them a shape. Now, how do we deal with the electron arrangement? When you're talking about the arrangement of electrons in atoms, the first thing you have to do is look at the way the periodic table is set up. There are 4 sublevels: the S, the P, the D, and the F. We just said that. The location of those on the periodic table and the total number of columns is listed. The S are the left 2 columns. The P are the right 6 columns. The D are the middle 10 columns. And the F are the bottom 14 columns. The number of orbitals, as we stated in the last section, there's 1s, 3p, 5d, and 7f. But when I look at that, there's kind of a correlation between the number of orbitals and the number of columns. The maximum number of electrons, if there are 2 per orbital, you have 2 columns, so there are 2 electrons, 1 orbital. 6 columns makes 3 orbitals, 6 divided by 2. 10 columns is 5 orbitals, and 14 columns is 7 orbitals. The shapes, as we just said, are spherical for S, dumbbell for P, cloverleaf for D, and complex for F. When you look at your periodic table, you'll notice that when I created this, I put it in chunks. Those chunks are the sublevels. On the left 2 columns is the S sublevel, but you'll notice one of the blocks is missing. Right next to hydrogen, there should be an element. That element is helium. Helium should be next to hydrogen when talking about electron configurations, but it's over with neon and the rest of the noble gases because it has more in common with them. Then the right-hand side, after you label the left as the S sublevel, if you look at the periodic table I gave you, at the bottom it says columns 1 and 2 are the S sublevel. On the right-hand side, this entire block of elements is the P sublevel, which is columns 13 through 18. Now notice helium is lifted off because helium is not a P sublevel. It is still an S sublevel. The center, 10 columns from 3 through 12, those are the D sublevel. And the bottom 14 are the F sublevel. So when I created this periodic table that I've given you, you notice that I have broken the periodic table into its 4 sublevels. Now, electron configurations for ground state atoms, meaning they're not element, or I should say they're not ions, they're just in their ground state, which is the lowest state. Now, to write Aufbau configurations, I'm going to show you how they work. You will not have to write them because all of the electron configurations are already on the periodic table. But if we were writing them out, to write Aufbau electron configurations, you have to use Z, which is the atomic number, and that is always going to be equal to the number of electrons in a neutral atom. So, if I were using my 1s, 2s, 2p, which is Aufbau, what I'm going to do is until you run out of electrons, you fill all the s's with 2's, all the p's with 6, all the d's with 10, and all the f's with 14, until the last sublevel can be a different number. So you'll notice I did 10. If you look for 10, it's number 50 on the periodic table. Now, if you count the superscripts that I've written already, 2 plus 2 plus 6 is 10, plus 2 is 12, plus 6 is 18, plus 2 is 20, plus 10 is 30, plus 6 is 36, plus 2 is 38, plus 10 is 48. So if 10 is 50 and I've done 48 up to there are 2 left. So it would be 5p2. Now, the 5p2 is very easy to know because if you look on the periodic table, you are in the 5th row on the right side, which is the p sublevel, in the 2nd column. Now I did it for zinc. I did all the inner ones maxed out. So I have 2, 2, 6, 2, 6, 2. That's equal to 2, 4, 10, 12, 18, 20. Well, zinc is 30. So 20 from 30 is 10. Now, if you were to go in the 3D sublevel, which is the center, and you go all the way to the right on the top row, you will be right there at zinc because you are in 3D10, which is the last column for the D sublevel. Now, rubidium. Rubidium, what I'm going to do is I'm going to cheat. I'm going to use tin. And if you look at tin, you see that tin goes all the way out to 4p6. So since the Aufbau does not change, and I know that all my inners are going to be maxed out, I can do that. And I go 2, 4, 10, 12, 18, 20, 30, 36. Well, rubidium is 37, so I need one more. Now, if I look at my periodic table, on the 5th row, S is the left side in the first column. That is rubidium, number 37. Now, due to the Aufbau configurations getting very long for elements with many electrons, you can use the noble gas before the element. So the one that is to the far right, those are the noble gases: helium, neon, argon, xenon, krypton, and radon. So basically, if I know the row that it's in, you'll notice I've rewritten tin, but I have brackets around 1s2 up to 4p6 because tin is in the 5th row. So I look at the end of the 4th row, and the end of the 4th row is krypton. Now, krypton has the electron configuration that is in the brackets. So instead of writing all of the inner electrons, all I have to do is find that tin's in the 5th row. So I look at my Aufbau configuration. The 5th row is 5s, 4d, 5p. The krypton is 36, and then 5s gets 2, that's 38. Then 4d gets 10, that's 48. And then 5p gets 2, there's my 50. The same thing for zinc. Zinc is in the 4th row, so I go to zinc, I find it in the 4th row, I move up one and all the way to the right, and I see that the noble gas before that is argon. Argon is 18. So if argon's 18, my 4s2 makes 20, and my 3d10 makes 30. Rubidium, same thing. Same krypton core as tin because it's in the 5th row, but it's the first element on the left side, so it's 5s1 because 36 plus 1 is 37. So if you are doing these, you might say, oh, this is starting to get confusing, but all of these are already done for you on the periodic table. So basically what I'm doing here is showing you how what's on the periodic table got there. So this is what we call an orbital filling sequence or an energy level diagram. And you'll see that it's the same thing as Aufbau, except it's written in 2 dimensions. If you look on the left, it says orbital filling sequence and it says increasing energy. If you are going through this 1s, 2s, 2p, it's the same thing as Aufbau that's on the bottom of your periodic table. The only difference is to the right of it, instead of just having 1s2, they have a box. And then 2s, they have a box. And then 2p, they have 3 boxes. And the d's have 5, and the f's have 7. So it's the same thing, it's just this is a graphical representation of what we just did. So what does a small box represent? An atomic orbital. How many electrons can each hold? 2, just like 2 shoes in a box. How many electrons can the D hold? Well, if you look, there's 5 boxes. So if there's 2 electrons per box, 2 times 5 is 10. Now, number 4, which is associated with more energy, 2s or 2p? So I look at my increasing energy. What is higher, 2s or 2p? So I look over there and I see that 2p is higher, so 2p is the one that has more energy. Now, to do 5 through 10, I'm not going to have the diagram, but you can look at yours. Which is associated with more energy, 2s or 3s? So I look along the side and I see that 3s is higher, so 3s is more energy. According to Aufbau, which will fill first, 4s or 3d? When I go up, I see the one that's going to fill first is the one that going from bottom to top, you touch first. So if I'm sliding up, I hit the 4s first because 4s is lower in energy than the 3d. Which orbital has the least amount of energy? Well, the one that's all the way at the bottom, the 1s. Why they have two lines for 1s, I will never know. Number 8, what is the likelihood of an atom containing a 1s orbital? 100%. It always is the first one filled. You can't go to 2s until you hit the 1s. Number 9 says sequence the following in the order they should fill. So if you're looking along the side, the first one of that listed would be the 4s. And then behind that is 3d, then 4p, 5s, 4d, 5p, 6s, and 4f. It's basically just reading across the Aufbau principle. And the general rule for describing the filling of orbitals, Aufbau's principle. You always fill the lowest one first. Now, using Aufbau sometimes can be incorrect. This occurs in some elements in the D sublevel and some in the F sublevel. Below are the assumed configurations for chromium number 24 and copper number 29. If I'm following Aufbau and I fill all my inners, I should get 1s2, 2s2, up to 3d4, because that would give me 24. Same thing with copper. I should have 4s2, 3d9 for my last row, because that would make 29. But what happens is those s electrons are in a lower energy and the d sublevel is stronger and higher energy, so they can steal one of the electrons to make them more stable. So what happens with chromium is one of those 4s2 electrons shifts up to the 3d, and it goes from 3d4 to 3d5. Same thing with copper. One of the s's becomes a 3d10. Now, don't worry about this, because if you look at the bottom on each of those, what I have done on the periodic table is the exceptions are easy to find. What I've done is I've highlighted them by making them a different color. So you're seeing all the different ones in the D sublevel that are what we would say exceptions, where they shift around electrons to be more stable. So don't worry about it. Just make sure that when you're looking at your periodic table, the only ones that you'll see that have the boxes around their electron configuration are the exceptions. Now, to do an energy level diagram using the electron configuration, it's very easy. And I equate this to going through a maze backwards. If we know the electron configuration, we can very easily do the energy level diagram. What I'm going to do is I have the whole energy level diagram written with the entire Aufbau electron configuration. So the first electron goes in 1s, so does the second. So now I'm at 1s2. The next one goes in 2s, 2s2. Then the next three, 2p1, 2p2, 2p3, to follow Hund's rule, I would do that. And then the fourth, fifth, and sixth for 2p6 would go that way. When we draw them, we draw the arrows in opposite directions because of the Pauli exclusion principle. And what that says is when you have two different electrons in the same orbital, they have to stay away from each other, and the only way is to have opposite spins. So then I have the 3s, and I have 3s2, and oh my gosh, why do I want to do all these? All I really have to do is work smarter. I look at my electron configuration. The last sublevel is the 6p sublevel. So everything before that is going to be filled. So notice I've drawn arrows for every single one of the electrons prior to that. And then I just put the first one in the first box and the second one in the second box, because Hund's rule says the electrons have to stay as far away from each other as possible. So what you do is you only put singles in. You can't pair them up until each one of those gets a single. So if I wanted to, I want you to just do this. Along the left side, I want you to write Aufbau, because the Aufbau is filling from lowest energy to highest energy from bottom to top. I also want you to pick any two of the filled orbitals that have an electron pointing up and down, the arrows pointing up and down. That's Pauli exclusion. So every one of those boxes that has two arrows is following the Pauli exclusion. And the last sublevel shows us Hund's rule. You will only ever see Hund's rule in the last sublevel if it's not an S. If it's an S, obviously, with one orbital, you cannot have that. Now, Atrium. To make this much faster, I've gone all the way up to 4D. So everything from 1s to 5s2 is filled. The only one that's left is my 4D. There are 5 different orbitals there, and the first one's going to go in the first box, which is the first orbital. So with that, you'll see that all you have to do is find the endpoint. Put that one in, and everything below it should be filled as long as it's not an exception. So I want to do germanium. So germanium ends with 4p2. So I've done everything up to the 4p, even including the 3d10. The first one goes in the first box, and the second one goes in the second box to make sure that you are following Hund's rule. You did not really see Hund's rule with the last one because there was only one electron. And last but not least, rubidium. It ends with 5s1, so look at everything up to 5s is filled. I throw that last electron. Come on, you're late. Let's move it. Get over there. He's taking his good old time. And the last one goes in the 5s sublevel. When we do ions, doing electron configurations for atoms, they're done for you. Doing the electron configurations for ions is what we're really going to be working on. When you do electron configurations, you have to remember this. Metals are going to lose. All of the green are metals. Nonmetals are going to gain. The nonmetals are listed in orange. So you can see that the nonmetals gain, the metals will lose, because what they want to do is they want to become just like the noble gases, which is stable. When you're doing electron configuration of ions, you have to remember this. Atoms will gain or lose electrons to have the electron configuration of the nearest noble gases. The nonmetals gain and the metals will lose. Transition metals will lose their valence electrons. Valence electrons are the outermost electrons, the s and p electrons. So a valence electron in a transition metal is only the s electrons, because the transition metals are in the d sublevel. They don't have p electrons. So I have 2 examples here. I have aluminum and strontium. They're both metals. Aluminum is neon 3s2 3p1. It is number 13. Aluminum forms a +3 ion. Now, you'll notice I have both of the electron configurations look the same. But something has to happen. Now, up above it says metals lose. So watch what happens to my neon 3s2 3p1. To form a +3, I have to lose 3 electrons. The 3p1 and the 3s2. They're gone. What's left? Neon, which, remember, when electrons are going to form ions, they're going to be the nearest noble gas. And the nearest noble gas to 13 is number 10, neon. Strontium, krypton 5s2. So what's going to happen? I'm going to lose the 5s2, and I'm left with krypton. Now, for regular metals, it's easy to see that. With transition metals, it's not quite the same. For anions, anions are going to gain. So sulfur and bromine are both nonmetals. So what's going to happen here is sulfur is 16. It's neon 3s2 3p4. The nearest noble gas to 16 is 18. So how do I get from 16 to 18? I gain 2. So watch what happens. The 3p has 2 spaces left because it's p4. It's supposed to be p6. So that 4 is gone, and it becomes a 6. Because let's count. Neon is 10. Plus 2 is 12. Plus 6 is 18. Well, 18 is argon. That's a noble gas. So when you have the same number of electrons as a noble gas, you are stable. Bromine's very close. Bromine's 35. It's right next to krypton, which is 36. Well, bromine is argon 18. 4s2 is 20. 3d10 is 30. 4p5 is 35. Well, I want 36 like krypton, so guess what? That 4p5 is going to become 4p6, which now I have 36 electrons, and that's bromine as an anion, which we call bromide. Same thing, sulfur as an anion, we call that sulfide. So, what happens to a neutral atom if it loses one electron? Why? When neutral atoms lose electrons, they become cations. They become a +1 ion because at this point, when you lose an electron, you have more protons in the nucleus than electrons in the atom. When the protons equals the electrons, it's neutral. What happens to a neutral atom if it gains? It's going to then become a -2 by gaining 2 electrons because now it will have 2 more electrons than protons. Because remember, neutral atoms have the same number of protons and electrons. A simple word equation that shows how you can figure out the charge of an anion given the number of electrons and protons is on your periodic table, and its charge equals the protons minus the electrons. So, what is the electron configuration for each of the following? In each case, also tell what charge the atom is likely to form in a bond. So, the first thing I'm going to do is beryllium. If you look at the bottom of each box, you'll see a charge. Above that, you see the electron configuration. So for the atoms, the electron configuration is easy. It's right there on the periodic table. Now, beryllium is going to form a +2 because the nearest noble gas to beryllium is helium because beryllium's 4, helium is 2. So what's going to happen is going to form a +2 ion. So which 2 is it going to lose? It's going to lose that 2s2. So all you're left with is helium. Fluorine, from the periodic table, it's helium 2s2, 2p5. Well, it's an nonmetal because it's on the right side. The nonmetals are on the right side. So it's going to form a -1 charge by gaining 1 electron. So when it does that, it's going to go from 2p5 up to 2p6. Argon. Argon from the periodic table is neon 3s2, 3p6. Now, what we said before was elements want to be like the noble gases. Well, argon already is a noble gas, so guess what? Nothing's going to happen. It's not going to form a charge. So its electron configuration is the same as the atom itself because it doesn't form a charge. Sulfur, it's number 16. It's a nonmetal. So I look at the periodic table and I see it's neon 3s2, 3p5. That's right underneath. It's 16. The closest one is 18, which is argon, which we just did. So it's going to become a -2 by gaining 2 to go from 3p4 to 3p6. Sodium, it's number 11. Its electron configuration is neon 3s1. Well, metals are on the left and they lose. And also, just remember this, the nearest noble gas to 11 is number 10, neon. So what's going to happen is it's going to lose 1 electron. Now it's going to have 11 protons and 10 electrons. So 11 minus 10 is +1. And guess what? If I throw away that 3s1, I'm left with the neon core. Nitrogen is number 7. And if you look on the periodic table, it's helium 2s2, 2p3. Well, it's on the right side and it is a nonmetal, so it's going to gain. And the nearest noble gas to 7 is 10, once again, neon. So what's going to happen is it's going to go from 2p3 up to a -3 charge by gaining 3 electrons. So now let's do the math. We have 10 electrons, we only have 7 protons. 7 minus 10 is -3. So there it is, that charge forming equation. So the 2p3 is going to become 2p6. Now you'll notice for every anion, F-1, S-2, N-3, they all end in p6. That is a given for the anions, that they're always going to end in p6, which is a noble gas. Now both of the metals just happen to have just noble gas configurations by taking away the electrons.